Okay, to recap, we're looking for the electric field, both magnitude and direction, necessary to support a free electron near the surface of the Earth. So we started by drawing our free body diagram relating the forces because it's an equilibrium. So in equilibrium, we know that the sum of the forces has to be zero. And since the force of gravity is down, the force due to the electric field had to be up. And since force electric field vector is Q times electric field vector, and Q is negative for an electron, that tells us the electric field direction has to be the opposite direction of the force due to the electric field. Hence, force electric field is up, so the electric field has to point down. So we got the direction already, points down, by looking at our free body diagram and the equation for electric force. Now we turn to Newton's second law. Sum of the forces in our vertical direction, which I called y, is zero, because it's an equilibrium. So I just make my equation, the force E, and I'm putting magnitude sign here just so we remember the signs of the charge and the E are already taken into account, minus, I'll put, just for completeness, the force of gravity in absolute value signs is equal to zero, which means that the magnitude of the charge times electric field minus mg equals zero. So we're trying to solve for the electric field magnitude. And then we just have to put in, what's the mass of an electron?
It's 1.602.
9.109 times 10 to the minus 31 kilograms. Acceleration of gravity. Look, I put 4 digits there and I only put 3 for acceleration of gravity. Everybody just puts 9.11.
I know the charge.
Okay, so what's the charge?
That's the 1.06 times
602.
602 times 10 to the negative.
Okay, so then we just have to multiply these together and we get the electric field magnitude.
I got 5.57 times 10 to the negative 11.
And what will the units be?
Force divided by charge. Newtons divided. Oh.
Yeah, that's force unit divided by charge.
So,
Go ahead, say.
No.
So putting this together, the electric field vector is equal to,
Okay.
It was 5.57, right?
Mm-hmm.
So there I got the direction with down. Bueno?
Mm-hmm.
The next one says the force between two charges.
It's 4 times 10 to the negative 9.
Force between two charges 4 times. There we go. Okay, force between two charges is 4 times 10 to the minus 9 newtons. If the magnitude of one charge reduced by a factor of 2 and the distance between the charges reduced by a factor of 2, what is the new force between the charges? So we've done something like this multiple times. It's just a new nuance in that we're changing both the charge and the separation. So I'll start by just drawing a picture. Here's Q1. Here's Q2. And they're separated by A. And that gives us a force. It doesn't tell us the direction, so I'm just going to assume they're both positive, and the repulsive force gives us a force Well, just call it force 1 equals K Q1 Q2 over A squared. Just use Coulomb's law, found the magnitude of the force. I assumed both charges were positive to give it a direction. So yes, I assumed a direction.
Should we always assume that?
It won't matter.
Okay.
Basically, you just have to make an assumption. Okay, so if the magnitude of one charge is reduced by a factor of 2, so that's Q1 over 2 now instead of Q1, and the distance between the two is reduced by a factor of 2 as well. So now I'm going to have Q2 is there with the separation of A over 2. Then what is force 2 equal to?
Q1, Q2 over 2A squared.
Say that again for me.
Q1, Q2 over 2A squared.
Okay, you forgot to say the K, but yes.
Okay.
But it's not Q1 anymore. It's Q1 over 2. Our charge is no longer Q1. It's Q1 over 2 now.
Okay.
But it's still Q2. And they're no longer separated by A. What are they separated by?
A over 2
squared.
Yeah. So now I have up here the value for K Q1 Q2 over A squared. So I'm going to take the numbers and separate them. So that's K Q1, and then I've got to have over here out front is a 1/2 for the Q1 over 2, Q2 over, and then this is going to be A squared over 4 on the bottom. And so I'm going to multiply by 4 over 1. Not
How did we get a 1/2 to?
Actually, I'm going to multiply by 4 over 4 so that I will have these cancel. And it's equal to, how do we get what first?
How is it that we're able to pull out the 1/2 to multiply it against the K and the Q2?
Okay, I will do this in longer form. Actually, there's no way to really do it in longer form. It already has it. Okay, so there's the 2 from the Q1 over 2. It's right there. So I still have the Q1 over 2. I just moved it under the big denominator. Right, so I took this 2 and just moved it to right there.
So it will give you the same number.
And then this here is A squared over 4 if you do the square.
Yeah, that makes sense.
And so when you have a division of fractions, this is the same as K Q1 Q2 over 2 multiplied by, you invert and multiply, so 4 over A2 or A squared. Right, that's how you divide fractions. So that's equal to 2 K Q1 Q2 over A squared. But what was K Q1 Q2 over A squared?
4 times 7. So it would be 2 times that?
Yes, which turns out to be 8.
That makes sense though, because if it's half the charge and half the distance.
The usual problems that people have with this is they think, okay, half and half, well, that's going to be the same.
Yeah,
Or, the options you could get would range from 8 times bigger to 8 times smaller, depending on how you do it wrong. But doing it right is going to give you twice the size. And so, I've tried to lay it out in the most mundane way you can do it. A lot of people would simply say, okay, you divide by a squared, or the separation squared. So if you cut that in half, that means you are going to multiply the entire answer by 4. And then you cut the charge in half, so that cuts the entire answer by half. So multiply by 4 divided by 2 is twice as big. Most people just go through it that way. But that's after they feel comfortable with it. And so I'm doing it in the,
Yeah, this is good.
Two uniform electric field.
Okay. 2 uniform electric fields are superimposed. There we go. Second one. Go ahead and scroll it. 2 uniform electric fields are superimposed. Uh-oh.
Not many people.
Quizzes in what class?
Advanced anatomy.
I don't know anything about anatomy. I would fail. 2 uniform electric fields are superimposed. The first electric field, E1 vector, is equal to 14 newtons per coulomb in the x direction. Right? The x hat means in the x direction. The second electric field is E2 is equal to 7.0 newtons per coulomb in the y direction. With respect to the positive x-axis, at what angle will a positive test charge accelerate in this combined field? So how should we start? Yeah, draw a picture. So I have my x and y directions, and then my electric fields are E1 is 14 newtons per coulomb. I'm just going to start at some random point, not at the origin. 14 newtons per coulomb. X hat. And E2 is half of that. There's my old man scroll. E2 is equal to 7.0 newtons per coulomb in the y direction. Now, if I put a positive charge, because it says a positive test charge. So if I put a positive charge here, what direction is the force going to be?
If you put a positive charge where?
Where it says Q.
Okay.
Going to start with, what's the equation that relates force with electric field?
The F equals Q1 Q2 or KQ1.
E.
It's just QE. It's just like we used 2 problems
the
ago.
last one.
So our force is just in the direction of the electric field. If I have 2 electric fields, how do I find the net electric field?
Subtract them.
Find both of them and
Add them.
You add them as vectors. And so the net electric field is going to be in that direction. And since the force is Q is positive, hence the same direction as the electric field, then all I need to do is find the electric field direction and I'm good to go. So what's the entire problem asking for? It's asking what's that angle? Because it says with respect to the positive x-axis. So, a big part of this problem is simply being able to interpret what are they looking for? And so you have to go through, okay, they gave me electric field. How's the electric field going to relate to force? What do I do when I have 2 electric fields? After you have those down, then you see, I'm just looking for that angle. So how would you find that angle?
A squared is B squared plus.
Okay, that would find you the hypotenuse or the magnitude of the net electric field. But all I'm looking for is the angle. I don't need that to find the angle. So it's not like that's a bad calculation. It's just not a necessary one. What do you say?
Would it be tangent? 'Cause you
Yeah.
have the opposite adjacent.
So we're just going to use inverse tangent of tangent is opposite over adjacent. So what's the opposite side?
E2.
Over the adjacent side?
E1 times
So inverse tangent of 1/2.
Oh, is that 14? Sorry.
Yeah.
I saw 10. Inverse tangent of 1/2. Oh, okay. 26.56.
So there we go. Our angle is 26.6 degrees. Y of x.
Okay.
This one is
You have an arbitrary distribution of negative charge. Let's look for it. I'm going to start at the top just, since I was one away. We have an arbitrary distribution of negative charge. Okay, so we have a sphere of radius r, and the charge is arbitrarily distributed. So that means we might have a big chunk of positive here, a small chunk of negative here, a big chunk of negative here, and big chunk of positive here, big chunk of negative here, and a small chunk of positive here. Okay, there is an arbitrary arrangement of charge. Now, this is not a uniform arrangement of the charge. So the electric field is going to be doing all kinds of wonky things because the charge is just, I'm sorry.
I was like, where is it?
Right. The electric field is going to be doing all kinds of crazy things because of the way the charge is distributed. You would have essentially the electric field is going to be coming out of here and going in there and coming out of here and going in there. Right? But we also know that we have a net charge that is negative. So if it's a net charge of negative, we're going to have more coming in than we have going out, because the electric field lines go into negative.
Mm-hmm.
Now, the question says, what if we go really far away? So we're going to go, okay, so you, so we go way over here now, and it should show up on the screen. And we say now the distance between those is 100 R. Now my picture doesn't do it justice, but you see there's my point. And so we're a long ways away. So if we're 100 R away, this now looks like a speck. So if we're really far away, the variations we see here don't matter. We're so far away from out here, it just looks like it's a little minus Q here. And so if it's a negative charge, I'm just going to see electric field going like that. Oops, change color. Because it goes into negative.
Mm-hmm.
And as far as I can tell, it's just a point charge because it's so small compared to how far away I am.
Okay.
And so since it's a point charge, I'm just going to have electric field is equal to K times that minus Q. I'm going to drop the minus sign because I'm just doing the magnitude over 100 R quantity squared. Right, KQ over R squared.
Oh, what I'd been trying to do the whole time. Okay.
So there's my answer. If they'd asked what the electric field was like 2R away, I would say I don't know because I don't know how the charge is distributed. But being 100R away, I say, okay, it doesn't matter how it's distributed because I'm far enough away, it just looks like a point charge.
So what determines, is there like a distance that would...
The rule of thumb is if you're 100 away, 100R away. So they put it right at that rule of thumb.
Okay.
Yes. You guys have class at 9?
No.
No? Okay. I thought you did, and I was like, yeah, because it's that time.
Another one.
SHW 4 now.
Okay. Going to SHW 4. And Ashley and I did that one last night.
Is it up?
Is it on here?
Yeah, it's, oh. I was like, it's right here. It's on my screen.
Oh, okay. Whichever one you didn't
Oh.
do.
We can skip.
Yeah, whichever one you didn't do, we'll do. You can look at it. Thank you.
Yeah, we have that one.
Okay, and those are the only two we did. So what do you want to look at next?
Mm-hmm.
You move a short Q from the RI 20 centimeter.
You move a charge Q from R1 equals 20 centimeters to R, or R initials 20 centimeters to R finals 4 centimeters from a fixed charge Q equals 10 nanocoulombs. What's the difference in potential for those two positions? So here's plus, or here's big Q. And we start with I can move it. R1 is 20 centimeters with Q. And we go to initial and final. My bad. So we go to that. We understand the layout? Okay, so how do I go about doing it? Tell me how to start. For a point charge,
Well, we know the full distance is 40.
potential energy is K Q1 Q2 over R, and voltage is defined as, remember, technically potential energy is a change. It's a change between R at infinity and this R. Likewise, voltage is technically a change, so it would be the change between R at infinity and this R. So the voltage due to a point charge is KQ1 over R. Implicit in this is potential energy equals 0 at R equals infinity.
Okay, so then would R be 20 because you're taking the final minus the...
Well, we have to do the final minus initial. We're not going to use delta R. We have to do the final minus initial.
Okay.
So we're going to have V final is equal to K. Which Q am I going to use here? Capital Q or lowercase q? Right, the potential energy has both, but the voltage, the electric potential, has only one.
What number are you guys doing? Where is it the...
Apparently it's number 5 on SHW4. Number 5 for my numbering, which is not the same as for yours necessarily. So which Q do I use?
Big Q.
Big Q, that's right. Because I'm looking at the electric potential due to that charge, the big Q, because it's going to be, and so that's over our final, and V initial is K big Q over R initial, and so the difference in potential is just the difference in those two.
Okay.
Now, I don't know if this is what you meant, Brittany, but you can see now that we're not going to use the difference in the two radii. We have to use the difference in the inverses of the two radii.
For the rate? Yes, that's what I meant.
Okay.
Oh, yeah, sorry. That's what I meant. I skipped over K and Q1 because I didn't know what to do.
Well, I had thought you had said it would be our final minus our initial.
Oh, no. Yeah, that's... thank you. That's fine. I don't have the rest of it.
So it's got to be minus 224.7 volts, I think.
Yep.
The one with the circles there.
Yeah.
Seriously.
Don't you when that happens, like it doesn't want to help? It doesn't want to work with you.
Apparently, it doesn't
when
want
you
to
do
get
it
any
with the
smaller.
Down here,
Hmm?
this here, if you do it like that, it makes it smaller. Right? Wait 1 sec. And it'll do it. See?
Okay. You just have to wait a long time.
Be patient.
It's my middle name. The first one is lack of.
Nope.
Alrighty. Using the figure, a proton is placed at point B and is allowed to accelerate when it reaches point C. What is the speed of the proton? So it goes from nyeh to nyeh. What is the information you have that's going to allow you to do this? Okay, you can't see it yet. Right there.
If you're patient enough, you can see it.
Yes, you just have to have faith. Okay, so what information do you have that's going to tell you what happens?
We have mass and Q.
Okay, so we have. I need to make my file name smaller because it cuts off my pins. Okay, so we have the mass and we have Q.
I'm looking for
We're not looking for acceleration, if that's what you mean.
We're looking for the speed.
Oh,
Mhm.
velocities. Charges as well. Voltage as well.
Looking for V final. What was V initial? You can say it out loud.
Zero.
How do we know that? It says is placed. Is placed is implying that it was
stationary?
stationary when it started,
Okay.
right? It doesn't say it directly.
So it's a play on words.
Not a play on words.
It's like
It's trying to make sure that students can read and comprehend,
okay.
but it requires, reading an implication. Okay, so what is going to tell us about the acceleration or the final velocity, right? Because you said A. What's going to tell us about that? And actually, we're not going to calculate the acceleration at all, but if we were back in first semester, we'd have two ways of solving a problem. What were the two ways? Find the final speed.
We could use acceleration to find the final speed.
Okay, what would we call that method? How would you find acceleration based on what's acting on it? I'm going to change the name of this class because it's driving me crazy. Maybe I'm going to change the name of it. It's got to be a way. Maybe there's got to be a way to edit it. Okay, I'm still waiting for you guys.
Mhm.
What's the nickname?
For the equations and equations. So I'm trying to remember.
No.
I don't remember.
I didn't look at my notes. I didn't bring my notes.
Right? I'll be back.
But I have like the whole entire list. I can come.
Well, no. You don't need to leave.
I'll be back. I don't think it is.
Equation.
Newton's second law. That's how we do it the way you were talking about.
Yeah.
Also,
It's just I forget
Newton's second law
Everything,
relates
yeah.
what's affecting it
Yeah.
to how it responds.
I just can't believe I forgot the name. Like we use Newton so much.
What would the second method be? Which is the one I always prefer and the one we have to use here. The only one we can use here.
Friction?
is that 1/2 something?
The other one that's
The really long
going
one?
to relate what is affecting it to how it responds. It's not really long. It's got 3 words.
the long equation.
It's the work energy relation. Right, so we had these 2 different methods for dealing with the dynamics problem. Dynamics problem is a problem where things are moving and we're trying to understand why. So, Newton's second law, we could find, maybe we could try to find the electric fields. And if we find the electric fields, we can find the forces, then we can find the accelerations, but then we have to also find the path because it's starting here and ending here. It could be doing a straight shot, but more likely, because it's a positive charge. So positive charge is going to be repelled by positive and attracted to negative. So it's most likely because the most positive is at the center and the least positive is outside. You would expect it to do something more like, I mean, why would it curve? I don't know why it would curve. I don't know why it would go that direction. What I really expect is that it would go like this.
Okay.
So why it went over to C, how it would get to C doesn't make any sense really, because these look like concentric circles. So the electric field lines should all be radial and it should just go like that. So I'm going to put C here and say that's where it ends. It doesn't end there because that doesn't make sense. But obviously the electric field is going to be changing because the distance between 500 and 300, well, maybe it is the same. 500 to 300 looks about the same distance as from 300 to minus 100. But if we use work energy, the path doesn't matter. And I think that's why they put C off to the side, because path doesn't matter then. And so if we're going to use the work energy relation, what is the work energy relation? Right? We have to know what it is before we can say, okay, so let's use it. Anyone? Work energy relation, we write 2 different ways. Yeah, that's not caught up with us. Just click on the screen. That's what I think works. The 2 things that you have for work energy relation are the net work is equal to change in kinetic energy, or the work non-conservative is equal to change in kinetic energy plus change in potential energy. The 2 mean exactly the same thing fundamentally because we break network up into non-conservative plus conservative, and we define change in potential energy as minus the work conservative. So they're exactly the same meaning. And so this one, the lower one, is the one that I usually use. So I look at this problem, I say, is there a non-conservative work being done on my particle? That is, do we have like a force of friction, or do we have somebody pushing it? The answer is no. The only thing acting on it is the electric force, which is conservative. So we have work non-conservative equals 0. And then change in kinetic energy is equal to, well, what does it ask us for the speed, right?
Yeah.
Okay, so 1/2 mass times speed final squared minus 1/2 mass times speed initial squared. But since we placed it there, that speed initial is 0, so it's really just the final kinetic energy minus 0. And then change in potential energy. And the change in potential energy is the only thing that's new to us. All this other stuff we've been doing. And we did, about yesterday, I guess 2 days ago, a whole bunch of problems where we did this. What's the equation for change in potential energy if I have a charge going from one electric potential to another. That would be if it was
Normally.
gravitational.
Yeah.
Right, that's why this is new. It's the only thing that's new because it's a different potential energy.
Yes. Q, E. I remember this one.
That's exactly what it is. Q times the change in voltage. So all we have to do is find the change in voltage and put these numbers in. So what is the change in voltage? What is VB equal to?
500.
500 volts. What is VC equal to? You can't see.
100.
It's minus 100. But let's... So delta V is equal to VC minus VB is equal to minus 100 volts minus 500 volts equals minus 600. Ran out of space. So I have my change in voltage. Now let's just put everything into our equation. So we're going to have 0, the work non-conservative, is equal to 1/2 mv final squared minus 0. That's my change in kinetic energy. Plus Q delta V. That's my change in potential energy. And we're solving for V final, so let us move the Q delta V to the other side of the equal sign. 1/2 mv final squared equals minus Q delta V. And then let's go ahead and multiply everything by 2/m. And that gives me V final squared is equal to minus 2Q delta V over M. So square root it. V final is equal to, technically there's a plus or minus when you square root, right?
Mm-hmm.
But we're just looking for how fast it's going. We're not worried about the direction, so we get rid of that plus or minus. It's a proton, right?
Yes.
And I think it told us what to use for the mass as well. Yeah, 1.67 times 10 minus 27. And it says to use 1.60, so let's get rid of that too, so we have the same answer as they do. Notice we had a minus 2 and a minus 600. We're going to have the square root of a positive value, which is good, because I did not expect an imaginary speed.
Okay.
Speed of light.
How do you square root that? Yeah, simple.
3.3, well, yeah, 3.39 times 10 to the 1, 2, 3, 5.
Such perfect lines.
Yeah, I've gotten better at that. Yeah, I've got to start getting ready for class, getting my demonstrations out and stuff.
I just had a quick question. So
Sure.
for parallel and for a series, isn't parallel, like at least when I was looking over the lab book, the parallel was like the whole thing added together. But then with series, it was in fractions.
We have to be more careful. Are we talking about capacitors or
I'm
resistors?
sorry. That's
Okay, so for capacitors, if you put capacitors in parallel, effectively you've added the areas together. And since capacitance is proportional to the area, you know that it's going to be getting bigger. You're welcome. And so for capacitors in parallel, you're just adding.
So if it were resistors, then it would be in the fractions, right?
Yep.
Okay. And then for series, would it be then in the fractions?
Yes. For capacitors that are in series, I should put a third one here just so. Oops. When they're in series, then you have the same charge on each one. And so you have a bigger voltage because each one of these is going to have a V is equal to Q over C. And so you have the same charge that's passed, but you have a bigger voltage because you have the three of them instead of just one. And so getting that bigger voltage for the same charge is actually decreasing the capacitance since, well, yeah. And so it turns out that 1 over C series is equal to 1 over C1 plus 1 over C2 plus 1 over C3, etc.
So if you have a parallel and then a series, would it just be pretty much the final would be 1 over, let's just say it's 2, and 1 and 3 are parallel, let's just say. So it'd be plus 1 over CP for this one over here, for the parallel one.
Write what you're talking about because I'm not sure I followed you. Well, here you can write it out.
Okay. So let's just say we have. This looks horrible.
Like my handwriting is beautiful.
It's like angels. Wait, it's little one and then a little one here.
Okay.
There it is.
Okay,
a
so-
battery. I was like almost forgetting there for a sec.
So we have, and so we want to find out what the equivalent capacitance is. So we start with these are in parallel.
Yeah.
How do I know I start with that? Because this is not in series with either one of these. It's in series with that combination. So I have to do that combination first. So I'm going to have this circuit becomes an equivalent circuit of where CP, because they're in parallel, is equal to C2 plus C3. And then that is going to be equivalent to C series there, where now I have to use 1 over C series is equal to 1 over C1 plus 1 over CP, which was C2 plus C3.
I did that same thing. I was like, I thought I understood. I was like, okay, so if this one is the opposite of resistors, I was like, then that would mean that this is this.
To give it a common denominator, I multiplied this one. Well, I multiply everything by C1 times C2 plus C3. And so that's why the top has C1 times C2 plus C3. And then this one here, when I did that, it became C2 plus C3, and this became C1. And so that's my final result.
I just feel pity for my drawing. It's like it's the worst one. Like you can barely understand it. If it wasn't because they were all huge lines, you would not understand it. Yes or no?
You're talking about
That one.
I'm fine with it.
I'm sorry.
No shame. Okay, so you understand what we did there.
Yeah. So then, like, if I would want to answer something, I'd put this answer instead of this answer.
Either one, well, You wouldn't put this
No,
because
no,
it says
this
CS
one.
equals.
Yeah.
But yeah, either one of these is correct.
Oh.
I mean, they're the same thing. It's just this one it's considered prettier writing, but this one's more economical.
Yeah, because like I wrote something. It had this here, this
Mhm.
one here, but I wrote it like this here, this part here, and I marked it wrong.
Oh, well, that's because it's 1 over your answer.
Oh. Okay, that makes sense. That's why it didn't give me any comment. It's like no comment. I was like, thank you. I appreciate that.
Alrighty.
Okay, thank you.
You're welcome.